Good morning from ASK Chemicals. Today we are recording this webinar on the topic of phenolic resins, specifically for wear-resistant friction applications. I will take you through this presentation slide by slide as we discuss this topic further. You will now see the agenda. We will discuss the technology itself and then go into results of our comparative study, where we have compared a conventional resin to a new technology that we have developed for wear-resistant friction. In this comparative study, we will look at Kraus test results. We will also look at constant pressure results to interpret the fade behavior. And then we will look at microscope photos of the surface to see the difference. And then in the end, draw a few conclusions. This next slide is to discuss the conventional ways that we would normally manipulate phenolic resins to get a better wear or heat resistance. You would know that from normal conventional knowledge that phenolic resins are often modified, and these can be various modifications such as epoxy modification, rubber modifications, metal modifications, or cashew oil modifications, but also one can manipulate the residual phenol monomer levels that are left in the resin. And lastly, one can also use additives to manipulate the resin. So in practice, in the friction application, how does this interpret into wear or fade behavior? If one wants a better wear or fade resistance, the basic theory behind it is that you would want a slower degradation or slower destruction of the contact patch or transfer film, or tribofilm, as some people may call it. Or secondly, you may need to leave more material in the contact patch. So these are the normal two methods by which you can achieve better wear resistance. I'm moving on to the next slide, and what we have just said would interpret into better wear resistance, fade resistance, or as some people may refer to it as heat resistance. In our study, in this comparative study, we have chosen a low metallic friction compound based on steel wool and mineral fibers. In this case, we have used and chosen a functional filler like wollastonite. Of course, calcium carbonate as a non-expensive filler, graphite and friction dust to balance the lubricant effect, barytes or barium sulfate as a heat-resistant filler, and lastly, the phenolic resin itself. You will note that the phenolic resin has already been optimized to a 6% level, which in the friction industry may be regarded as a well-optimized level. We look at the hot press molding conditions and the oven post-curing conditions. In the case of the hot press, we have chosen a top and bottom platen temperature of 150 degrees Celsius, a total pressing time of 5 minutes, inclusive of 3 degassing cycles. For the oven post-curing, we have chosen a regime or a program whereby we heat to 100 degrees Celsius, hold it for 1 hour to give time for the moisture to escape. We then heat to 120 degrees Celsius, hold it for 1 hour again to make sure that the ammonia gases from dissociation of hexamine has escaped. It is then further heated to 140 degrees Celsius to facilitate the cure further, and finally to a top temperature of 180 degrees Celsius for the final post-curing, where we hold it for 2 hours. This slide shows us the testing standards that we have chosen, which is well known throughout the industry, because these are the normal testing standards. In our case, we did test the hardness, as well as shear strength, density, retention, constant friction in line with the ECE 90 protocol. The Kraus testing equipment was internal equipment that we used. And then finally, we also tested compressibility of the friction compound in the matrix. Here we show the physical test results that we obtained of the older technology, what we call a reference here, compared to the new wear-resistant technology. You will see that in hardness as well as in compressibility, one can see a softer matrix from this modification that we have done. And it then interprets well into the shear strength, which is substantially better with the new technology. Density and retention is quite stable and comparable. And as I said, compressibility slightly improved at lower temperature as well. And I do point your attention to the significant improvement in shear strength as well. We will now next discuss the test results, the performance test results. And first we look at the Kraus test results of the older technology, again what we call the reference. What you will see here on the screen in the top graph, and you will follow my pointer, the top graph is on the red line, the temperature line, showing 150 degrees Celsius test method, test condition. You will see on the secondary y-axis on the right, 150 degrees Celsius, and the blue trend line being the friction coefficient on the primary y-axis. What we see here at 150 degree test condition is an initial slight green fade, and as applications continue further, the fade behavior continues. In other words, a reduction or slight reduction in friction coefficient over the number of applications. In the bottom graph, if you follow my pointer, you will see that the test condition was run at 350 degrees Celsius, and the friction coefficient at 350 degrees Celsius shows quite substantial green fade or initial fade, followed by over recovery as the over time. This kind of behavior of initial green fade followed by over recovery, of course, is not ideal. One would prefer that the trend at higher temperature should resemble, to at least within about 10%, the curve at lower temperature. Now let's look at the wear behavior of this older technology. On the right hand side, again, if you follow my pointer, we express the wear as grams per brake horsepower hour per specific gravity, And in this case, we obtained a number of 0.32 under cold conditions. In other words, 150 degrees Celsius. If we look at the wear under hot conditions or 350 degrees Celsius, what we call drag conditions, the wear gives us a number of 1,78, 1,79, and we'll keep these two numbers in mind as we now look at the comparison with the new technology. We'll keep in mind 0.32 and 1,79. This next slide then shows the cross results of the new technology. And immediately you can see that at the 150 degrees Celsius test, the friction coefficient is quite stable in the initial applications. Slight green fade again, and good recovery. We compare that to the results at 350 degrees Celsius, where the friction coefficient shows a slight initial green fade with a good recovery, and this recovery is well within the 10% tolerance of the 150 degrees Celsius test, which is, if you interpret it that way, a very good behavior or a desirable behavior. Let's move on to the wear behavior. And now we see on the right here a number of 0.19 at low temperature. And if you compare that to the number of 0.32, now you sit at about 60% of the original wear compared to the old technology. But then look at the behavior of wear at high temperature, 350 degrees Celsius. You have a number of 0.6 compared to the previous number of 1,79, and which is about a third of the wear of the older technology. So a substantial improvement in wear resistance. Next, in the next slide, as I move forward, we will look at the fade behavior in this test where we conducted constant pressure testing. And again, this is the reference for the older technology. The top graph simply shows the temperature profile, and the bottom graph is really what we are interested in. You will see that older technology typically, and one might recognize this as a typical behavior, that the friction coefficient drops off at the end of the application as the temperature increases. And that is exactly the definition of fade. As the temperature increases, every time we see a drop off or loss of friction coefficient, which is fade. On the right hand side, you can look for yourself, there are the corresponding friction coefficients. Let's compare this to the fade behavior in the new technology, and immediately you can see a substantial difference. The crest of the wave, or the applications, the friction applications, the crest of the wave does not fade away or fall off in each case. Every time as the temperature increases, the friction coefficient is held very well up to the end of the application. This means that with this new technology, it shows a marked improvement in fade resistance as well, with the corresponding friction coefficients again on the right hand side. Lastly, we want to show you microscopy photographs or micrographs of the surfaces of these friction disc pads. And you will see on the scale at the bottom here, it says 200 micron. In other words, this is about a 3 millimeter cross section photograph, again, of the old technology called the reference. And immediately you can see a substantial wear behavior in the form of plowing effect. You can see the plowing effect across the surface, and you can see the worn away binder matrix, or the matrix in total. We then move across to the new technology, a micrograph of the new technology. Again, same size surface of about a 3 millimeter cross section. Immediately you can see a difference in the degradation behavior of the surface being much smoother. The surface remains intact or more intact. And this refers directly to the degradation behavior of the matrix, or the binder holding the matrix together much better. Finally, we want to draw a few conclusions in each case for this comparison. If we look at the older technology, we saw in the cross testing at high temperature green fade, and we saw over recovery. And also in colder temperatures, we saw a low friction coefficient. This kind of behavior, or a fade of green fade followed by over recovery, is an undesirable performance and not up to standard or requirement. We also saw a relatively high weight loss or wear with the older technology. And now I want to draw your attention to the conclusions with the very latest technology. What we saw in the cross testing was initial green fade followed by very good recovery within the 10% variation limits of the friction level at 150. We saw that the wear rate was only a third compared to the reference. In other words, about a 66% improvement in wear resistance. If we look at the cold temperature or lower temperature performance, we saw that the wear rate was about 60% compared to the older technology, which, in other words, interprets into a 40% improvement in wear resistance. You may also recall that there was a substantial improvement in the shear strength with this new technology. That concludes the first part of the presentation, and I will take the next few minutes to quickly introduce you to an oversight of the ASK Chemicals as a company, as I introduce a few details of the company itself. Of course, we are a truly international and internationally represented company with a global footprint. You can see with 18 facilities around the world, the revenue size of the company around the 650 million euro per year mark, with R&D facilities also around the world. This next slide, without going into any of the details, simply shows you our commitment to innovation, and more so into sustainable innovation. Some of the examples here shows innovation into the areas of low free monomers or low residual monomers, performance improvements, as well as total cost of ownership improvements. The next slide shows our representation around the world with our head offices in Hilden in Germany, close to Düsseldorf, sites in orange all around the world, northern and southern hemisphere, R&D centers in Germany, North America, Brazil, South Africa, and India. And you can see in the blue color in which countries we are represented. Here's a quick overview of the market segments we represent around the world. In this area of industrial resins, it covers all the known market segments such as abrasives, friction, insulation, composites, impregnation, uh, refractory, which is closely related to the foundry market. Finally, also into structural timber and plywood, fertilizer and biodegradable fertilizers, and also binders for paints and coatings. We close off this presentation with the contact details. I invite you to scan the QR codes, and if you have any questions, technical questions or portfolio questions, to address it to these two gentlemen. That concludes our session on wear-resistant phenolic resins for the friction industry. I thank you for your time and take care.